Hi everyone, and thank you for listening to this presentation if you're doing this, and let's hope it's one of the very last, that we will soon meet all in person to do these things, but yeah, we do this as long as needed. So the talk of today is inertial spin dynamics in ferromagnets, which some of you may have listened to it already, so I've been giving this at a few conferences, but there is some new data, new exciting results I will show in the end. So it's the same work, but with some final addition, which I think we will find very interesting if you're interested in this type of problems. So this is the photo of my group that we took right before the pandemic hit. We had our kickoff meeting in Venice. But the work I'm going to talk about today was mostly performed by Niraj, who is the PhD student, who's now going to graduate very soon here, and then also Nana and Debanjan. Nana, another PhD student, Debanjan postdoc in my group. So before we dig into the results, so why do we do this type of research? Well, the motivation, that the big picture motivation is related to the need, the increasing global need for data and for energy efficient data, because even though it's not yet one of the major drivers of energy consumption, I mean data, it's the one with the highest derivative. And we learn, unfortunately, this pandemic, how exponentials easily realize like a small number very quickly escalates to something which goes out of control. And this is one of the areas where we risk the most. And just to give you a figure, which I always find astounding this is around quite a lot, but it still surprised me, but you can check, it's actually quite impressive. 300 Google searches, something as simple as writing a word into a search engine can cost the energy needed to boil 1 liter of water. So 300 of those Google searches. And given there are billions of searches every day, that's not a negligible source of energy consumption, and it is increasing. And so it's very clear that within 1 decade, given the more and more people on the planet will have access to fast data and to videos, these are actually videos are the big, so where the data is largest, that's where the consumption is larger, of course. That's going to be a problem. So we need to try to solve this. Of course, there are some solutions that are closer to realizations, although really the basic way information is stored in a big data center with magnetic hard drives still is a technology that's rather old, and there seems not to be a cheaper and more reliable solution coming up here. So we need to go back to fundamental research and try to see if we can get hint of we can do something new. And one of the things that we do in my group, but of course other people do around the world, is to use light to study and control materials. Here, this is a very nice picture or animation from an article in Quantum magazine, where they show like very artistically like how a bunny turned into a horse thanks to laser beams. Of course, this is like a very pictorial representation, but the idea is that we can not only understand, but also maybe make materials with light that would not exist in thermodynamic equilibrium. So it opens up a phase space where we can explore properties. And people, of course, the usual argument is, but this, if you need like a giant laser which consumes a lot of energy to do this, then you're not winning anything. Well, that's true, but there's also, at the same time, it's a static view of how technology evolves. I mean, now this is not even the most recent picture, but you can have femtosecond lasers which are very compact and very efficient. And maybe as we started with the computer, it's not going to be something that everyone is in his home, but a data center could, given the total energy spent, could see possibly like a use of laser if this would turn out to give you a total gain in the energy consumption. So one has to be careful in both ways, I think, when you do this, because there are technological advances that really make a revolution, like lasers did in many other areas. So I think it's still scientifically correct to try to explore these possibilities. And the reason we want to use lasers is because femtosecond lasers were used now 25 years ago to show that you can actually quench the magnetization of one of the ferromagnetic materials, in this case was nickel, but of any 3D metals that are used in magnetic hard drives by a lot, by 50% in less than a picosecond. This is what is plotted in this figure. So the remanence of the material, let's say, let's call it 100%. This is just deviation from the saturation, but let's say full remanence then is quenched in less than a picosecond and it recovers. This was surprising at the time because this is not, it's not written in any, it was not written in any textbook, textbooks of physics that this could happen. These things should happen at a much lower rate. And of course, this was a quenching, but what we really want to technology is to be able to write information with light. This was shown like a decade later, and that's represented here, where you can see two magnetic domains, white, let's call it pointing up, and black pointing down. If you come with light pulses, in this case was opposite helicity. This is now, at the moment, that's not important, but what I want to say, what is important to see here is that with single laser shot, so a single laser pulse is able to reverse from black to white and from white to black the magnetization of this material. So there was a lot of interest, and I hope that maybe we can use light for data storage. But this has been also in the 25 years one of the most investigated, also least understood phenomena in modern quantum physics. It's a highly non-equilibrium process, and we have still, we start to have some answer, but a clear answers or a general understanding of how angular momentum is dissipated at these ultra-fast timescales, how spin angular momentum is dissipated at these fast timescales is still lacking. So that's why we're still investigating this. And so in my group, but also in other groups, so one of the tools that actually change a bit the paradigm and allows us to understand a bit more what happens in these systems beyond what can be seen with in a tabletop with an optical laser are the laser facilities that are able to produce X-rays, so which were added to the temporal resolution of femtosecond, also the nanometer resolution of the X-rays. So if these are phenomena that happens at the nanoscale, you need also the nanometer resolution to really understand, because the spatial inhomogeneities, spatial structure of what's happening, it's important to understand how things take place. And not only this, so the XFEL, Fermi, and LCLS are these X-ray machines, but there is also been a recent development on electron-based or like accelerator-based sources of terahertz radiation. And the work I'm going to talk about, actually, in this case, has made use of the terahertz radiation generated at TELBE, which is an accelerator-based source. What this source does is creates relativistic electrons that at an energy, of course, lower than the electrons that you need to create X-rays. You accelerate them and you let them pass through a series of an undulator, which is a series of alternating magnets, which deflect the trajectory of the electrons, and in deflecting this, the electrons radiate. And given the lower energy of the beam and the period of the magnets, you can tune it to actually get emission in the frequency range that you want. And in this case, we did terahertz. Then you get rid of the electrons here in green, and you collect the terahertz radiation and you send it to a lab. In this case, it's like the lab is upstairs from the source. And how does it look like? So you can actually measure the electric field that you generate with different techniques. But you basically can see that the emitted field resemble basically the period of the undulator. So here there was, I think it was 12 poles. So you have about 12 cycles of oscillation. So the number of cycles is constant in this when you generate this way. So if you change the frequency, the total duration of your pulse changes. So in this case, here is shown that you go from 0.15 to 0.9 terahertz. And you can tune this. The nice thing of these machines is that just by tuning the energy of the electrons and of the magnetic field, you can really change this frequency in a nice way, in a controlled way. Okay, so why did we use this this machine? Okay, so the reason is that we wanted to better understand I don't know if I'm saying something that is historically incorrect, but I would say it's probably the most famous equation of magnetism. I don't know if Heisenberg would agree with this, but I would say the most famous equation of magnetization dynamics, I mean, is the equation of magnetization dynamics, which is the Landau-Lifshitz-Gilbert equation. And it basically states, as I think for this audience, this is maybe not necessary, but if someone new into the field is coming in, so this is basically, it's a differential equation, a first order, which has two terms, which tells us that if you have a magnet with a certain magnetization and you apply a field, you have called an effective field, which can contain different terms. If they are not collinear, what will happen is that the magnetization will start to precess around such effective field. But this, so in theory, this would go on forever, but in reality, there is always some dissipation channels, and this dissipation described by this alpha parameter called the Gilbert damping will actually make the precession to align, the magnetization to align with the effective field. So if you combine these two together, you basically get like a damp, a damp precession, or like a precession which spirals towards the effective field. This is a solution of the LLG equation. And this is the equation that describes how the switching in data centers, in magnetic data centers that I was describing in the beginning happens. So you have a bit one information, which is north pole up, apply magnetic field, you flip it, and through a precession you reach the other state, which is going to be a 0 or a south pole. Okay, so this is all good. This has been used. This kind of works. It's proven that it works every time something is written to a hard drive in the world. So, but there is a big problem. It's actually this equation from a physical point of view is incorrect. It has a completely unphysical inertial tensor. So Gilbert, so the same Gilbert in the equation, noticed that this was a problem. And in a review in 2004, wrote explicitly, actually in a footnote of this review, he said, I was unable to conceive of a physical object with an inertial tensor of this kind. And the reason of this statement is that because if you think to classical mechanics, there is no object that you can think of which has all but one parameter on the inertial tensor which are not 0. The closest you can get is to get, for example, to a rod rotating around its axis, or even at extreme, but where it has all but two elements that are not 0. But all element but 1, 0, that's not, it doesn't exist. At least we cannot picture this. And this was a bit surprising to me. I did a PhD on these topics, and I never thought about this because we give it for granted. And also you can ask yourself, how can it be wrong if it's being used every day in data centers? And of course, the answer is that this has to do with the approximations we do. So if whatever this very gross approximation that you make is related to degrees of freedom, which are very well separated between each other in energy, so then you can forget about the other degree of freedom and assume that the equation is good enough. And this is, so this kind of explains why it works, but it's generally not correct. And the intuition, the person actually thought how to do this in a formally correct way was Jean-Éric Vegros, which rederived the full equation using a Lagrangian formalism. And he got, of course, the same, it has to be a very similar equation, but with one extra term, which has the second derivative of the magnetization in it. And basically, it looks like the first part is exactly the LG, but what is extra is this term. And what this term does is that instead, the solution, instead of looking like I showed before, the damped procession, now if you include this, there is also a notation and on top of it, which is actually, if you think about it, if you think of spinning top, this is exactly what you would solve mechanically. This is what you would expect. Is there is in a 3D rotating object, there is precession notation. The Earth has precession and notation, so it has to be. It has to do with the conservation of angular momentum. And the new parameter that came out of this equation is this tau. It's what's called angular momentum relaxation time, which is related to the time it takes this notation to damp and to relax, basically. And the value of this was not known because, I mean, you read the equation, but what is the value of tau? But of course, it was pretty clear that somehow, since we were not able to notice it before, it had to be somehow a tau which led to notation which were a much higher frequency than the FMR. Because we detected the FMR, if there would have been a slower notation, we would have seen it. So, but if the notation happens at a much higher frequency, it could be that we may have missed it, because doing spectroscopy in the pico femtosecond regime is something that we can. It's a bit more peculiar. It's not the typical gigahertz spectroscopy where you have like a commercial device that can help you to do this. So the story was actually, I like to tell the story because I think it's a good example of how science sometimes works. I had no idea about this, but at the Ultrafast Magnetism Conference in 2017, I met Jan-Erik, and I was completely fascinated by his talk, because I said, wow, I completely missed this, and I found this as a fascinating fundamental problem that we maybe can now attack. And the reason why I thought this is because I had some data in the drawer which I could never explain. That it was like you say, oh, someday I will think about it, and then we will see. Where I saw in a 3D ferromagnet where I could measure FMR and so on. This was done with in a pump probe setup with terahertz fields that I was learning to use when I was a postdoc. And I saw this 300 gigahertz oscillation with a system that had an FMR of a few gigahertz. And at first, of course, I thought it was an artifact and so on. So I said, but this was very much reproducible, but okay, I don't understand it. I'll leave it there. Someday I will think about this. And then this came to my mind. So when I met Jan-Erik, said, okay, but let's try to do this. Now we have this new source at Telbe. We were being early users of the machine, also because it was just built. So let's try to do this. This seems to be a very fascinating experiment, and now we can do it. It was not possible just a couple of years before. So let's try the forced oscillator experiment, where we swipe the frequency of intense terahertz field, and we can detect, since we do this with a coherent radiation, the amplitude and the phase of the response. And so since Telbe was starting, I said, okay, well, let's propose this and let's try to see if we can detect such a notation peak. And so, yeah, so we went to Telbe and we did exactly what I just said. So this is basically show that we can sweep the field and then go in this range, which was not explored before. The way this is done, so you get the terahertz pulse, as I showed before, from the accelerator, which gets collimated and then focused onto the sample. So this is the terahertz field. There is this optics, is called parabolic mirrors, that are needed to focus broadband terahertz fields. There are no good lenses for this, so that's why you do this unusual. But this is basically only focusing optics. And then we probe. So we have near-infrared laser, which is synchronized with the terahertz field, which we send, and it goes through a delay stage. So if those arrive always at the same time, we can change the relative time of arrival of terahertz and pump and infrared probe by moving mechanically this delay stage. Then we go into the sample, we reflect off, so we are in the polar Moog geometry. I will show you this a bit more later. And then the light gets reflected back, goes to the splitter, and then we measure the rotation of the polarization of the light. So we measure the magneto-optical Kerr effect to detect the magnetization. If we zoom in on the sample, so what you see here is that, yes, probe coming in and getting reflected back. And here, but this most importantly is the pump. So the way we were setting the magnetization was to apply a magnetic field bias, a slight bias, just to saturate the sample in plane. So this blue is the magnetization of the sample. And then we had the polarization of the tera's magnetic field. So electric field was in plane, but magnetic field was out of plane, so that the M here cross H term, so they were orthogonal, so we had the maximum torque out of the plane. And we started to check if this made sense, and it did, in the sense that we were doing the experiment we wanted to do. So if you measure the Mach response as a function of time, so where you vary the delay time between terahertz pump and femtosecond optical probe, you can see that you see nice oscillations, which are maximized when your magnetization and your H terahertz are perpendicular. If you put them parallel, so you can easily rotate the polarization of the terahertz with a wave plate, then you see zero. So this gave us a confidence that this is indeed a M cross H type of dynamics. Okay, so, and then what we wanted to say, I said we wanted to do a forced Lorentz oscillator experiment. And the idea is that, so this is again, it's a physics 101 course, so in mechanics, is if the idea of a mechanical oscillator. So if you are below the resonance frequency, you have an oscillation which is between the driving force and the and your spring, in this case, which is mostly in phase and of small amplitude. If you're at resonance, what happens is that you actually get the largest amplitude and you get a 90 degrees phase shift. And if you're after, then the amplitude goes down again, and you are completely out of phase. Okay, so this is classical mechanics that at play. So we try to do this with magnets. And we did this. We did this actually on 3 different samples to check that this was correct. Here I show just for not making the slides too crowded, but it's published on the paper. So we could see that moving the terahertz field, let's say between 0.4 and 0.8 terahertz, we could see that the oscillation was smaller or relatively smaller at 0.4 terahertz. It reached some sort of maximum 0.6 and then went down again. So it was the first suggestion that there seems to be a modulation of the amplitude. And the way you normalize this, it's actually very crucial. So you need to be careful when you do this. So in the paper, we explain how we did it in the correct way, because there is a lot of things to be taken care of. But we did that, and we're pretty confident on this. The other thing we could look at, it was the phase response. So as I said, so if you are before the resonance, you should be in phase, and if you're at resonance, you should be 90 degrees out of phase. And that's, so what we saw, I take again these 2 frequencies, 0.4 and 0.6. You can see that 0.4, what you have green is the experimental data. The pink is the simulation that we did, which goes on top of it. And the driving force, this is not simulation, this is actually measured with an independent measurement. So we can measure when the terahertz field arrives. And we can see that they are basically in phase within the noise. But when we go close to the maximum, then we start to see something which is pretty close to 90 degrees. And in the supplemental material of the paper, we show all the frequencies and all the data. And again, here only for simplicity, but we would see we see that if we go to 0.8 or a higher frequencies, then the oscillation is completely out of phase. So this is we measure a force response of something. Okay, and so what is this something? So if we compare now, you take all the experimental data and we do this this plot. So we take the FFT of the response and we plot the amplitude, and we fit with a Lorentzian. We see that for all the 3 material that we looked, there was a cobalt iron boron film, and then 2 different crystal instruction of permalloy. We see that indeed there seems to be a resonance at, let's say, between 100 between 0.5 and 0.6 terahertz, so 500, 600 gigahertz, which is 100 times to 1,000 times any no resonance for this material in these conditions. So this is what could be. And also the interesting thing is that the peak seems to be slightly offset. This is what this line shows between the permalloy and the cobalt iron boron. So it seems to be a material dependence of this peak. And so the obvious conclusion is that, okay, this could be really the signature of an annotation. And yeah, I just want to comment that this is this is a very time-consuming experiment. I mean, it looks like okay, why we don't improve the data acquisition and so on, but each point is a 6 hours acquisition, and we did this 3 times over a year, so it was 6 months shift to make sure that we're not fooling ourselves. So because this was really a new evidence, but we did this 3 times and mixing the frequency, that the order of the frequency we probe, so that we don't go into some drift of the machines that you have to be careful with. And it's a giant amount of data that gets generated, because every single shot of the terrace which arrives, and we measure millions of them, we measure it and we correct for the time and stability of the accelerator, and we have a phase stability of 10 femtosecond, which is much higher than what is needed to prove that there is a phase shift. So this basically, so after this we say, okay, there is really a resonance peak, and if you solve with simulations the inertial energy equation, you actually show this peak. You actually get this peak, and so the conclusion that we saw the notation. One thing that we noticed now is pretty clear here, that somehow the line width doesn't match. So this, we actually now understand what's made be happening. We didn't know at the time, so this is an open question in the paper, but with a new result, we will show in a couple of slides, you will see that there maybe is a hint to what is going on there. So the point is that if you calculate this angular momentum relaxation time, this is, I give now the value of tau in the way the equation was written before. There is some other people in literature that prefer to, instead of using the tau as it was written, do not group the alpha, the damping out in the way the equation was written. So this value, if we convert in the other standard, there will be something like 300 femtosecond. I think since it's so new, we are learning how to write this. But let's say the 10 picosecond here is like 300 femtosecond in the other convention. So, but what is important here is that this is not important for slow switching. So as long as you do this switching in hundreds of picoseconds, like in the data centers, you're fine. You can use the LLG without the inertial term. But when you go fast and when you go ultra fast, so like we do now, this you cannot neglect. And where does these terms come from? A bit from a microscopic point of view, it was shown by the work of others, but I think the full derivation was done by Peter Oppener in Uppsala, is that the higher order spin-orbit coupling terms in the Hamiltonian would lead to this term. So yeah, so this is where it comes from, and we see now notation, natural oscillation in the table with in the lab with a tabletop source. Basically, so the problem with this experiment, or the difficulty with this experiment, of course, we had the field always on when a notation was taking place. So, but what we can see now, we improved the way we can do the experiment in the lab. So we increased the field strength, and now we can hit the sample quite hard and see now how it relaxes. And then we were able to learn a few things more. A curiosity, this is just, I found fascinating that the ratio of magnetic notation and precession frequencies is roughly the same as the one of the Earth. It's about 1,000 times smaller. So the notation is and precession are related by that factor. And it will be an interesting coincidence for the other Gilbert who wrote the De Magnete in 1600, who thought that the planets were kept together by magnetic forces. This would have been a coincidence that he would have thought it would prove this point. And over Newton's later work. All right, but this is the work. So this is the artistic representation of what we observed. And this is a paper. There was a lot of co-authors who all deserve to be there, because when you do these experiments, which are so complex and new and requires only new instrumentations and new ideas, it's really like need to have a big team. So I'm very grateful for all them because they did a fantastic work in making this happen. Okay, so just to conclude very briefly, so to dig a bit in the what I said in the last slide, the conclusion. So spin notation inertia, when does it matter? I think I really like one of the pictures that was put forward by Alexei Kimmel and co-authors when they looked at the inertia-driven spin switching in anti-ferromagnets. So we were for the first time to observe it in a pure ferromagnet, but in anti-ferromagnets was observed. And the picture is, which I find very very nice to visualize when inertia matters, is that if you imagine a double well potential with a particle, a ball with no mass, your stimulus will need to be as long as the time needed for the stimulus to bring the particle above the potential maximum. So, and then you could leave it. However, if you have inertia, you could use impulsive stimuli, and then this would basically kick the particle, the ball, on the other side. So this already suggests, so you can imagine the difference between having a feather and a steel ball into a potential wave. So if you have a feather, you need to bring it all the way up, otherwise it will not continue by itself. But this would do it. So it suggests here that if you, when you go to short time scales, that when it matters. And we recently did work. We have a manuscript which is on the archive, is under review, where we try to actually study this switching in a ferromagnet with the with inertia. So solving the inertial energy equation and see what happens if you apply a short magnetic field, short intense magnetic fields, and see how it switches. And the thing that we observe is that we can distinguish two ways of switching. The first one we call it processional. And the second, ballistic. These are terms that have been used in literature, but sometimes in an equivalent way. So we call procession the one where you actually observe the procession, and ballistic where you basically, with your field paths, you really bring the magnetization the other way directly. And here we show what is the switching time versus, here is basically the product of the field amplitude and duration. Okay, so full width and maximum in picosecond of the pulse width. So it's a Gaussian pulse, field pulse, which we apply, and then we create a 2D phase, 2D diagram, and we explain this. But basically, the long story short is that with if you compare the LLG and the inertial LLG equation, what you see is that it is easier. You can get easier into this ballistic regime, which is the fast one. So the procession switching, it takes much more time than what we call a ballistic regime, which it's here. In this, when the switching time is much faster. So if you go this direct way, it's much faster. But it's easier to get into this regime with the LLG. So the orange curve is before the blue one. But then once you're there, so once you cross the potential, the inertia, it makes this region, this ballistic region, much more robust. Then if you increase the field again, then you will bring the magnetization the other way, and you will get precession back to the other state. And also the switching time, the nice thing about this ballistic region doesn't depend on the field. So in a way, the inertia indeed gives you a larger stability region for the switching. So, and I mean, the paper it's a simulation paper. We give a lot of details. I think we also describe the energetics of the process in an intuitive and nice way. So if you're interested, I recommend you to read it. One of the most exciting things we saw now in the lab, and this is what I was mentioning before. So now, as I said, we can do with single cycle pulses, Terrace pulses, we can drive the coherent Terrace dynamics. And now we studied materials. This is a cobalt films, epitaxial cobalt films with different anisotropy. So those are FCC, BCC, and HCP. So we studied the 3 phases of cobalt. And the cool thing, and we chose this because those are films with large magnetocrystalline anisotropy. So we want to see if we can enhance this by looking at these materials. And indeed, to a great surprise, it's surprising that we could see it actually. I wouldn't say it was easy because it's small, but after the Terrace pulse arrives, this is the force coherent response broadband. What you see, if you zoom in into the trace, and we did this also with looking at the frequency analysis, you actually see tiny oscillations here. And the cool thing is that those are the natural oscillations. So we could fit the damping directly from here because we don't have the forced oscillator. We don't have to assume the Gilbert FMR damping. And actually shows up this. We'll soon put this paper out. That it seems that the damping at terahertz frequency is much larger. So you cannot use the Gilbert damping to the Gilbert FMR damping to explain the dynamics here. So if you assume the Gilbert damping is larger, these frequencies, probably because the scattering mechanism at the different energy scales are different, then you can fit this. And this would explain also the line with the disagreement in the paper. The cool thing also is that the mutation frequency here, I only plot part of the result, but basically you can see that the oscillation of the green curves are much faster than the one on the of the blue and orange. So basically, and what we can see is that this is the HCP sample, which has the strongest magnetic crystalline isotopy in our films. And so basically, so the mutation frequency is much higher when the magnetic crystalline anisotropy is larger. And it's still visible, but it's less. This is about 2 terahertz. It's about 1.3, 1.4 for the other two. For the 2 cubic phase, we get similar precession frequencies, and for the hexagonal one, we get a much higher one. So I think this is very exciting because it starts to test another hypothesis of the microscopic theory of nutation, which is indeed is a spin-orbit coupling. In this case, we correlate to the magnetic crystalline anisotropy. So, and with this, I finish, and I thank you for your attention.